So let's talk about the role of fast physical optics technology in the simulation, in the modeling and design of optical systems that contain diffraction gratings and diffractive optical elements. Now, we have selected two examples to highlight today, to discuss today. But before we do that, before we move on to these examples, I want to say a few words. I want to summarize the key aspects of this fast physical optics technology as it relates to the topic at hand. And the main takeaway here is that fast physical optics simulations are made possible by the connecting field solvers philosophy or approach. This, in a nutshell, means that when we are going to tackle a complex system, we're going to break up that system into smaller pieces, and we're going to select different electromagnetic field solvers, different algorithms, to simulate the interaction of the electromagnetic field with each of those parts of our system. And then we're going to bring these solvers, these different pieces of the system together in a seamless, non-sequential way in order to obtain the solution to Maxwell's equations for the whole system. The first example that we're going to be talking about today is provides a perfect platform to discuss this and acts as a perfect illustration for this. We're going to have a system that combines free space propagation, traditional, typical lenses, and a microstructured, nanostructured wafer. What we're going to do is we're going to select one solver for the free space propagation steps, a different solver for the smooth surfaces that define the lenses, and yet another solver for that wafer, for that grating, that periodic structure. And then the engine is going to put the solution of these algorithms together in a seamless, fully non-sequential manner, and that is going to solve Maxwell's equations for the whole system. In the second example, we're going to showcase the design of a diffractive optical element, a DOE, and here, once again, the whole discussion around the topic of the electromagnetic field solvers and having different field solvers available comes into play, albeit in a slightly different way as before. Because here we're going to perform the initial structure design of our DOE with a given field solver that is an approximate solver. And the actual setup that we're designing does not strictly fulfill the assumptions of this initial approximate solver, but we still use this solver because it provides a very straightforward mechanism for that structure design to go from the functional design to having an actual physical structure that will that can be used in a physical system. Then afterwards, we're going to refine this initial design for which we used an approximate solver. We're going to refine this initial design with a rigorous solver, and we're going to use furthermore the programmable capabilities in Virtual Lab Fusion to analyze the behavior of the structure in detail, see where the initial assumptions of that approximate method break down, where they fail in this particular situation. And we're going to characterize the behavior of the design, and we're going to see different ways in which it can be improved. This right here is Virtual Lab Fusion, the fast physical optics modeling and design software, and we're going to dive straight into our first example, the optical system for the inspection of a microstructured wafer. And that's what we have on screen right now, is the optical setup file for that system. And I have pre-run the results of the simulation so that we can discuss everything more easily. But I think I will also let the simulation run live at the end so that you can see just how fast it goes. And let's take a look at the path that the light follows using the 3D ray results profile, which is very similar to a 3D ray tracing simulation, but the ray tracing engine, or what could be discussed as a ray tracing engine in Virtual Lab Fusion, is actually also obtained as a consequence, as a direct consequence of fast physical optics. So there's a lot more to it. But for convenience, I might just use the words ray tracing in the webinar. So we start here from our source. That's going to be a fundamental Gaussian mode, with a frequency of 266.08 nanometers. So that's outside the visible range. So the color that we're actually using for the illustration here for the ray tracing result of the ray tracing visualization is just for visualization purposes. The frequency, again, is not inside the visible range. So the light emanating from this Gaussian source is going to be redirected by this first component towards a high NA objective lens. The NA is 0.9. And this objective lens that we have right here is going to focus this incident field onto our microstructured wafer, this component 20, this component number 20 here, which would be located right here in the focal plane of our objective lens. So this is the first part of the propagation of the light through the system. For this first step, of course, we don't make use of the full NA of this objective lens, but that will come later. Then, let me minimize that again, we actually look at the light. Let me hide coordinate systems here. Then we are going to collect the light that is reflected by our wafer, again this component here, and because we're talking about a periodic component, a grating in short, that light that is reflected by that grating can be characterized as a set of discrete orders. And there may be more, according to the period of the structure, I'm not sure, there might be more orders, probably there are. But because of the finite aperture of the objective lens system that we have here, only 3 of those orders, from the minus first to the plus first order, are going to be collected by our imaging system. And that's what we see in this ray profile simulation. Then these 3 orders propagate further through our imaging lens here, the final imaging lens, and onwards, and this part of the propagation is quite long, onwards to the final detector, where we're going to recreate an image of that wafer. What I want to mention here, first of all, is that this simulation is fully non-sequential. So you can see that the objective lens is just located here in the building of the system, in the building of our optical setup. So we have just once this objective lens. But when the light is reflected by this grating element here in this propagation step, it's going to travel back through this objective lens. So the connections actually in this representation, this schematic representation of the optical system, just give us an idea or tell us what element is going to provide the coordinate system reference for the subsequent one. So this here means that I'm positioning the grating with respect to the coordinate system that is provided as a reference by this previous element, the objective lens. And what this connection, this red connection here means is that this final lens is going to be positioned in a reflection, so backwards from this element here, using the coordinate system provided by this grating element here. That's what the connections mean. But the engine itself, is the non-sequential engine, is going to actually find where the light goes, independent of what we tell it with these connections. The connections are just there for positioning. So let's minimize that. And one of the important aspects of virtual light fusion is that it consistently models the light as an electromagnetic field, as a vectorial field with 6 components, 3 electric and 3 magnetic components. And we do that consistently from the source onwards. That means we can take into account polarization effects at all the steps in our system. So we're talking about circularly polarized light in the source, the first thing that we're going to be looking at is the electromagnetic field, or rather the electric field. We could look at all the 6 components, but we're going to focus on the 3 electric ones. And we're going to be looking at that electromagnetic field here, which is the focal plane of this objective lens before the light has had the chance to interact with the grating. So we're just going to be looking at the electric field at the focal plane of this objective lens in that incident way towards the grating. And that is, I believe, what we have here. So this is the EX component, the amplitude of the EX component. We work with complex valued fields. That means we have access to the amplitude and the phase of all the 6 electromagnetic components. Then I can go through the different components here. This is the EY component. Because the light was circularly polarized at the beginning and the system is rotationally symmetric thus far, both components look the same, both EX and EY look the same. But we also have an EZ component. It's not very strong in this case, but it is there. It's not very strong because this part of the propagation is relatively paraxial. We're not making use of the full numerical aperture of that objective lens system, but it is there. We have a longitudinal component that is a result of the light being focused. And we can actually look, I'm going back to the initial component EX. We can go back to EX or EY, and I can click here on equalize scaling, and we can actually take a look at the relative importance of that EZ component, because we have the same scaling for all the 3 electric components, and we can see that in this case it's quite faint. But it is there, and it's taken into account in the simulation. Now, just for illustration purposes, I ran another simulation again at the same plane. This is the electric field at the focal plane of that objective lens before it interacts with a grating with a wafer. Only in this case, I'm using linearly polarized light along X at the source. It's still a fundamental Gaussian mode, but it's linearly polarized along X instead of circularly polarized, as was the case with the previous result. Now, in this case, we have the EX component is a main component, and then we can again go through all 4 of them. There is a certain amount of crosstalk between EX and EY because of the local dependence of the transmission and reflection coefficients at the surfaces of the lens. This crosstalk effect is very, very small. And we're going to do again that equalized scaling trick afterwards to be able to see just how faint, how weak this effect is. But it is there, and it's taken into account by the simulation. And once again, we have a longitudinal component, EZ, because we're talking about a focal plane. It's also faint, but this effect is stronger than the previous one. So I can go back to EX, click on equalize scaling. I go back to EX because this is the scaling that I want to use throughout, because this is the main component. And then we can sweep back to EY. It's not even visible. This effect is very, very weak. And onwards to EZ, we can see something, but it's also very faint. So this gives us an idea of the importance of the vectorial effects with respect to the lens, also the polarization state of the source. And it's just a way in which we can investigate those polarization effects in the system. In this case, they are not very strong so far, but the grating or gratings in general tend to have a behavior that is strongly dependent on incident polarization. So the response is very polarization dependent. And because we can trace that vectorial behavior, or because we trace that vectorial behavior consistently through the system, that means we're going to be able to get to the grating with actually the vectorial components that we have that we actually physically have there, and to compute that response in a rigorous way that takes into account the combination of all those vectorial effects that may happen in the system. So now let's take a look at our wafer. I double click on this grating component and let's look at the structure. So this is one period of the structure and it's invariant in the other direction. This is the X dimension, it's invariant in Y, and this other dimension would be Z. So we have again a sequence we have several materials having that play a role here. We have gold, we have molybdenum, and we also have air filling the gaps between the structure or the profile of this wafer. The period is 410 nanometers. I close here. I close this window, and let's talk a bit about the solver for the grating specifically. We're going to be using, for this example, a rigorous solver for periodic structures that's called Fourier Modal Method or rigorous coupled wave analysis. It's known by both of those names, FMM, RCWA for short. And typically, this solver takes one wavelength, one incident direction, that is an ideal plane wave, and calculates the Rayleigh coefficients for per outgoing order for that single incident ideal plane wave. Now here, the incident field is not an ideal plane wave, it is a focused field. It's not very strongly focused, but it is focused nonetheless. So if we were to use just one single run of the FMM, the results would not be accurate because we would not be taking into account the full incident field. But here we can take into account the fact that the incident light is focused onto our structure, and we do that here by using 11 times 11 incident directions to compute the interaction with the grating of the field with the grating. That means we perform 11 times 11 runs, individual runs of that FMM solver. And by doing that and combining the results, we can actually characterize in the response the fact that the incident field is focused and not an ideal plane wave. If the incident field was very collimated, very paraxial, we could get away with just using a single point here. But because we focus the light onto that structure, we need to make use of this feature. And then we also define here under channel configuration the orders that we want to take into account in the simulation. So we're interested in the illumination from the front side, and we're just interested in the 3 reflected orders that are going to propagate back through our objective lens, that are going to be collected by our imaging system and are going to finally contribute to the formation of the image. The next step is we're going to look at the irradiance at the plane. Remember, we're traveling in reflection, so we're traveling backwards in the system. So we're going to look at those 3 orders right before they enter the objective lens as they propagate backwards towards the detector. So for illustration, we're going to look at the 3 orders at this plane here, right before they enter the objective lens. That corresponds to this detector. And once again, I have those results generated. And we can see the 3 orders, our central order and the minus first and plus first order here. This is a radiance, this is a radiometric quantity, a radiometric magnitude, which can be calculated as a function of the electromagnetic field. So that is also the beauty of having the access to the full electromagnetic field, is that we can actually compute any result that can be defined as a function of that electromagnetic field that includes all radiometric, all photometric quantities, and we do so on the basis of that electromagnetic information, electromagnetic field information that reaches the detector. And we do so in this version, which was released at the very end of last year. We do so with the new add-on concept. So if I go to this detector, we see we calculate the Poynting vector on using the electromagnetic field information, and from that Poynting vector we calculate the irradiance, and finally we deliver the irradiance, which is what we just saw. And we can add any number of add-ons here. Now, to conclude, we're going to go all the way to the image plane of the system and look at the reconstructed image. It's going to be, it's not going to be a perfect image, of course, because we're just looking at three diffraction orders. But we're going to see that the asymmetry that the structure exhibits, if we go back to the wafer structure, once again, we can see that it's not the same as we advance from left to right than when we advance from right to left. So that asymmetry is going to be visible in the image that we recreate as well. And that is this result. So we can still see, we can still intuit the Gaussian shape of our initial beam, but on top of that, superimposed on top of that, we have an image of the structure of the wafer, of our wafer. And I have extracted the cross-section here along X so that we can look at that more easily. And this result corresponds to that linear cross-section of this, again, irradiance that we have calculated at the detector plane. And here in this 1D cross-section, the asymmetry is very clear. But just to emphasize the fact that that asymmetry of the structure is reflected in the image, I have generated another system where that structure has been mirrored. So it's exactly the same system. The only difference is that we have mirrored the structure and we have generated the results again. And this is the irradiance at the image plane. Once again, this is for the original structure and this is for the mirrored structure. And this is the 1D cross-section extracted along X. And finally, just for convenience, I have superimposed those two cross-sections, those two 1D cross-sections, to reveal that asymmetry more clearly and how that asymmetry is taken into account in the image and is clearly visible in the image. So it's not the same result if we work with the original structure or with a mirrored structure. So this example really brings a lot of technological pillars of the software together. The importance of the connecting field solvers technology, in the fact that in the sense that we have both lenses and gratings. If we try to use a rigorous a rigorous Maxwell solver for the whole system, we would be out of the game. It's unfeasible. It's not a question of having a simulation that lasts a long time or a simulation that requires a computer with a lot of computing power. It's a question of just not being able to perform that simulation. So having this connecting field solvers technology is extremely powerful, as is revealed here. And also that non-sequential engine that allows us to set up our system as it is physically, just define the different positions, and then the engine is going to find the path followed by the light and perform the simulation on the basis of that non-sequential behavior of the light in the system. As I said, I'm going to run the simulation once from beginning to end. We're not going to generate these results in the middle. So just from the source to the detector at the image plane of the system. And we're going to be working just with a mirrored structure, just because it was here right at hand. And I'm going to run the simulation with our fast physical optics engine, with our general profile, and we're going to look at that irradiance, and it's just going to take a few seconds. And remember, we're taking into account polarization, we're taking into account the interaction of that focused field with all vectorial effects included with the microstructured wafer, and we're propagating back towards the detector plane, and we have the results, and we got it in 16 and something seconds. So I think this really highlights very nicely the power of our software, of Virtual Lab Fusion. And this is just the result that we were looking at before, only with a different color scale. If I set it to reverse rainbow, we have exactly what we had previously. That's it. That's all I had to say about this first example, and let's move on to the second one. So up next, the design and rigorous analysis of a non-paraxial diffractive beam splitter. And the task is going to look something like this. We start from a Gaussian-shaped input beam with wavelength 632.8 nanometers and a waist radius of 1 millimeter. Then, for this incident light, we want to design a 1 to 7 by 7 diffractive beam splitter that has a binary height profile that is made out of fused silica, and on the pixel size of which we already have a certain restriction that's going to be 300 nanometers by 300 nanometers, and the overall thickness of this diffractive optical element is going to be 1 millimeter. As regards the outgoing light that we want to obtain as a result of this design, we want, as that name 1 to 7 by 7 beam splitter already tells us, we want to obtain from a single incident beam, we want to obtain a regular array of 7 by 7 spots, and we want those spots to cover a total extension in the direction space of 30 degrees in X and 30 degrees in Y, and we want that to happen with a separation of 5 degrees between orders. Now, we're going to use a series of design approaches that rest on a paraxial assumption, and while the input beam is indeed paraxial, the outgoing light isn't. So we're going to use a design strategy that the assumptions of which we actually know we're going to violate. However, in order to preempt the possible errors that we may incur by knowingly using an approach, the assumptions of which are not entirely fulfilled, we're going to perform, after we do the design, we're going to perform an analysis of that design using a rigorous solver, a rigorous electromagnetic field solver. This rigorous solver is going to be the Fourier Modal Method, also rigorous coupled wave analysis, FMM RCWA, the same solver that we used before in the wafer example. And we're going to use these rigorous results to find out the effects of using that erroneous paraxial assumption about our system in the design step. And the whole process is going to start with one of the design wizards that Virtual Lab Fusion provides with its Diffractive Optics Toolbox Silver Edition. Now, I have not spoken a lot about the license model that you would need, or the license that you would need to actually simulate the examples that I have been showing. But just very briefly, the rigorous solver for periodic structures, the FMM RCWA, is included with Virtual Lab Fusion Advanced. So for the first example, the wafer example, you would just need Virtual Lab Fusion Advanced. For this example, because we're also going to be using that rigorous solver in the analysis step afterwards, in the second part of the example, We also need Virtual Lab Fusion Advanced. And then for the design part at the beginning, we need the Diffractive Optics Toolbox Silver Edition, because that carries the design algorithm IFTA, the Iterative Fourier Transform algorithm, that we're going to use for the design. So as part of that Diffractive Optics Toolbox Silver, we have several wizards. That means a document that takes you step by step and asks you to enter the values of the different parameters that are known about your system and about the design that you want to perform. And then it produces a pre-configured IFTA document with which you can perform the design. So that is the sequence of steps here. And for this example, we select the regular array beam splitter design wizard. And that's what we have here. Now, we're not going to look at everything in detail, but just to give you a peek into what kind of parameters you would have to enter the values of in this design wizard. Here we have the description of the incident light, where we enter the wavelength and the waist radius, and then a few steps forward, we can define the number of orders that we want to produce. We're talking about beam splitters, so we know we want discrete orders, and the separation between those orders. And already at this stage, this validity control in the design wizard is going to tell us that the diffraction angles that are required for the generation of the desired light pattern are larger than 10 degrees. So we're already being told that the assumptions of the methods that are going to be involved in the design are not fulfilled by the parameters that we have entered. We know this, and we are going to ignore it for the time being, but I just wanted to point out that you are given this warning already at this stage. So as a result of this wizard, once we have entered all the parameters we know, we would get the IFTA document that we can see on screen right now. And once again, this would be generated in a pre-configured state after filling in that wizard previously. And this IFTA document allows us to perform multiple runs. Because there is a certain randomization in the process, each time we perform a design with the Iterative Fourier Transform algorithm, we're going to get a different result. And the multiple runs will automatize that process. And this is a good idea because then we have a series of designs, and the trained eye of the optical designer can say, okay, I prefer this design over this one because it would be easier to fabricate, for example. That is one possible reason. So we have used this option of the multiple runs in this example, and as a result, we get these three different results. So each of these is one run of that design algorithm, or what comes out of one run of that design algorithm. And what we're looking at here is the phase distribution of the transmission function for one period of the structure. We're talking about generating discrete orders. That means we're going to need a periodic structure. So we're looking at just one period. And one example of what I mentioned just previously, the fact that here we have a very small feature in this first design, and the trained eye of the optical designer might say, I would prefer not to use this result because I know that smaller features are harder or more costly to fabricate. So you are presented, as a result of those multiple runs, you are presented with a choice of different designs, and you can use your experience to choose between them or select a few and perform further analysis, which is what we're going to do in this case. Now, we have these phase distributions of the transmission function, and now we want to generate an actual physical structure from this. And to that end, we're going to use a thin element approximation, which also rests on an assumption of paraxial behavior. So both the IFTA and the the thin element approximation, rest on assumptions of paraxiality. So I would select each of these designs, and I would go to this Design tab and click on Structure Design. And I would get then the structure simply by entering the wavelength, the design wavelength, and the value of the refractive index for the material that I want to use. And the reason why T is so convenient here is because it provides a very straightforward way to generate a structure from such a transmission function, because it's going to assume a proportional relationship between the phase and the height of the structure. So we do that, and as a result we get 3 different systems. And that's what we see here. Let me put a bit of order. Each of these systems contains the corresponding structure for the 3 designs or the 3 phase distributions that we previously designed. Let's just take a look at that. For design number 1, for example, I go into the component and I want to take a look at the height profile of that structure, and I have it here, right here. We can see that there is a proportional relationship between the height of the structure and the phase of that transmission function. So that's basically what the thin element approximation did here, and the same for the 3 designs. And now I want to use, for the analysis of the performance of my designs, I want to use a certain set of merit functions that do not come inbuilt with virtual lab fusion. So what we have done here is we have used a programmable grating analyzer to calculate, on the basis of the rigorous results of the FMM or the RCWA, the merit functions that we need in order to judge the performance of our element. And so that's what the code looks like. We're not going to go in detail through it, but we're going to show the total efficiency, the average efficiency excluding the 0th order, the 0th order efficiency, the 0th order error, which is basically comparing the efficiency of the 0th order against the average efficiency, the uniformity error, and the uniformity error excluding the 0th order. And the reason why the 0th order has such a protagonist here in these merit functions is because one of the points where the failure of the paraxial assumption in the thin element approximation is most readily visible is in the efficiency of the 0th order. And that's what we're going to see from the results in a second. So now we have gone back to the presentation where we have put all the results of the simulations and the analysis together. And we're going to go briefly through these results. What we can see at the bottom left corner there is the efficiency for all the different orders that emanate from the structure. So it's a bit of an abstraction. That's what is represented here. The abscissa and the ordinate correspond to the order index. So the central point here is the 0, order, and the color gives us the information about the efficiency of that order, with 100% efficiency being the total that is put into the system by the incident beam. And these results correspond to the predictions of T, of that paraxial approach that we used for the structure design. So we first perform our analysis with this approximate solver with T. And in this table here, we see the results also of the merit functions that we programmed, that we implemented in that programmable grating analyzer. On the next page, we have the results the same results, but this time using the rigorous solver. And the first thing we see is how the 0th order in all three cases jumps a lot higher in terms of the efficiency. That's what we just discussed, of the 0th order efficiency being one of the points where we most readily see the failure or the breaking down of the thin element approximation approach when the system is no longer paraxial. And we can also see how the values of the merit functions are affected once we use that rigorous approach. So in case of design 1, the 0th order error, which compares the efficiency of the 0th order against the average efficiency of the system, jumps from over 3% when we use T, that approximate method that assumes paraxiality, to 452% when we use a rigorous approach. So the next step in this example is to perform an analysis. We're going to vary mostly the scaling of the structure, the total scaling of the structure, which is one of the parameters that has a lot of impact on the efficiency of the 0th order. And we're going to study the behavior of the three designs as we vary this height scaling of the structure. The aim here, of course, is to improve the uniformity. Let me go back. The orders, the working orders, the orders that we're interested in are the 7x7 central orders, as we know from the design. The others are straylight, the ones with the lower efficiency that we can see around that central part. Those are straylight. And so these curves, for example, are the result of a parameter run in virtual lab fusion, and we're plotting three of those merit functions that we implemented in the programmable grating analyzer. So the 0th order error, for example, the uniformity error, and the uniformity error without that 0th order. And the abscissa in this case is the height scaling. So we're investigating how that height scaling influences the uniformity of the system, particularly with particular emphasis on the 0th order. What we see on this page is that simply tuning the scaling of the structure is not going to have a big impact, is not going to noticeably improve the behavior of design number 1. Design number 2, however, shows more promising results to this particular analysis of varying the height scaling. Now, just by varying the scaling, we're not going to be able to affect the uniformity of the other orders. So what we hope to achieve with this variation is to minimize the efficiency of the working order so that it no longer negatively affects the overall uniformity. And again, we see more promising results here, a more promising response to that height scaling than in the case of design number 1. And design number 3 was the one that also initially had a 0th order that wasn't that dissimilar to the efficiency of the other working orders. However, as is explained on the slide, it's also a good idea to perform an analysis of the impact of varying that height scaling, if only as a tolerance analysis, in case fabrication is not able to achieve exactly the height that we have designed for. What would the effect of that be on the final performance of the manufactured element? So that's another reason to perform this type of analysis, not just to improve the design, but also to analyze how this design that we can, of course, configure with ideally fixed parameters in a simulation environment, how does it behave in the face of real live errors and variations from the parameters that we want. With that, we wrap up the presentation and let's start the Q&A.